menyediakan layanan penelitian dan pengembangan riset. Hingga tahun 2020, terdapat 10 dosen dan 2 staf untuk membantu pembelajaran 300 mahasiswa di program studi ini. Kolaborasi penelitian juga dikembangkan melalui network antar institusi. Program studi teknik material dan metalurgi ITK akan terus berkembang untuk melahirkan sumber daya manusia yang unggul dalam kompetensi bidang rekayasa material dan teknologi bahan, tidak hanya demi kemajuan industri, melainkan juga pengabdian masyarakat yang berkualitas.
Demikian pengenalan program studi teknik material dan metalurgi. Sampai jumpa di pertemuan selanjutnya.
If I could run with you, and from what I have heard,
laboratorium terpadu ini menurut saya itu ide yang sangat baik.
I wanna say forever, we could be good together. Guess mystery loves company. Better too late than never. You know we could do better. So take a chance and run.
Komunikasi di Indonesia ini sangat kotor dan tidak efisien. Padahal banyak bahan limbahnya itu yang bisa digunakan untuk harus ada asosiasi branding pada suatu disiplin atau suatu prodi terhadap itu jadinya apa. Kami percaya di Kemendikbud kalau kita melakukan kebijakan yang kita juga harus anggaran di balik kebijakan itu gitu. Nah main-main gitu.
Diawali dari keinginan pemerintah Indonesia untuk memenuhi kebutuhan sumber daya manusia di luar Pulau Jawa, berdirilah sebuah perguruan tinggi negeri di jantung kota Balikpapan bernama Institut Teknologi Kalimantan. Diresmikan oleh Presiden Republik Indonesia ke-6, Susilo Bambang Yudhoyono pada tanggal 6 Oktober 2014, Institut Teknologi Kalimantan memulai kegiatan akademik dengan menerima mahasiswa baru sejak tahun 2012. Dan terhitung sejak 5 September 2019, jumlah mahasiswa Institut Teknologi Kalimantan adalah sebanyak 4.074 mahasiswa. Desain infrastruktur. Pengelolaan sumber daya air dan manajemen proyek konstruksi dipelajari dalam program studi teknik sipil. Identifikasi potensi masalah wilayah dan kota, serta menyusun rencana tata ruang didalami dalam program studi perencanaan wilayah dan kota. Pada program studi matematika, selain mempelajari aljabar, geometri, dan analisis, matematika juga berpeluang untuk mempelajari statistika, komputasi, aktuaria, dan riset operasi. Institut Teknologi Kalimantan juga menginginkan lulusan yang dapat berperan menjadi konsultan dan sistem integrator, database specialist, dan IS academician yang dilatih dalam program studi sistem informasi. Prodi Informatika mempelajari bidang dasar informatika, pemrograman komputer, serta mampu mendayagunakan, mengevaluasi, dan mengidentifikasi pengembangan sistem berbasis komputer. Tergabung dalam jurusan Sains, Teknologi Pangan, dan Kemaritiman, program studi Fisika, Teknik Perkapalan, dan Teknik Kelautan, bersama mengembangkan sumber daya manusia melalui mahasiswanya dengan mempelajari sifat-sifat fisika yang ditujukan untuk mendukung industri, konstruksi dan kekuatan, hidrodinamik, dan sistem perkapalan, hingga kemampuan dalam merancang, mengembangkan, dan menganalisis struktur bangunan lepas pantai. Institut Teknologi Kalimantan juga mencetak mahasiswa yang memiliki kemampuan di bidang konversi energi, industri pertambangan, manufaktur, robotika, dan otomotif melalui program studi teknik mesin. Mahasiswa yang memiliki peluang kerja pada bidang kelistrikan yang mencakup pembangkit tenaga listrik dan sistem jaringan distribusi melalui program studi teknik elektro. Proses dan cara mengubah bahan baku atau mentah dan bahan kimia menjadi sebuah produk komersial dengan memanfaatkan proses-proses kimia maupun perubahan sifatnya dipelajari pada program studi teknik kimia. Lulusan teknik industri mempelajari bagaimana cara merancang, menganalisa, mengaplikasikan, dan mengintegrasikan beragam faktor industri yang mampu bekerja dalam bidang operation, plan, quality control, hingga industrial manager. Tergabung dalam jurusan ilmu kebumian dan lingkungan, program studi teknik material dan metalurgi mempelajari tentang sifat mekanik, fisik, dan kimia bahan logam, komposit, plastik, dan keramik, serta aplikasinya terhadap berbagai bidang. Sebagai dedikasinya terhadap lingkungan, Institut Teknologi Kalimantan membuka teknik lingkungan yang mempelajari semua penyebab permasalahan di lingkungan, mulai limbah padat atau sampah, bahan berbahaya dan beracun, B3, hingga limbah cair. Sebagai wadah pengembangan diri mahasiswa, Institut Teknologi Kalimantan menyediakan unit kegiatan mahasiswa diantaranya Asma Warman, Rik M. Enggang, Futsal, Basket, Tenis, Voli, Badminton, Seni Budaya, Kopma, Fokus Point, ITK Musik, Paduan Suara Mahasiswa ITK, Fox, Pramuka, Gangga Yaksa, Developer Student Club, Spekta untuk Sang Pencipta, dan Bumetam.
Selamat datang di ruang kelas kampus Institut Teknologi Kalimantan. Mata kuliah kita kali ini adalah pengenalan program studi teknik material dan metalurgi.
Pernah terpikirkan tidak, mengapa gigi palsu bisa aman dipasang pada rahang seseorang bertahun-tahun lamanya? Kenapa motor kuat menahan beban kita yang berpuluh-puluh, bahkan beratus-ratus kilogram beratnya? Apakah material laptop ini sama dengan motor tadi?
Kayaknya nggak kuat deh materialnya.
Sadar atau tidak, perkembangan HP dari zaman dulu hingga zaman sekarang semakin canggih, tapi semakin ringan. Hai Kak. Kok bisa dari kebutuhan kacamata yang tebal untuk menembus diganti dengan plastik tipis yang disebut softland? Sadar atau tidak, kemajuan teknologi berangkat dari perkembangan material. Pertama-tama, kita menemukan besi atau metal di alam, lalu kita menemukan plastik atau polimer, sampai akhirnya kita menemukan keramik. Tidak cukup dengan ketiga jenis material yang berdiri sendiri-sendiri, kemudian kita menggabungkannya dan ditemukanlah komposit. Kemudian pertanyaannya berubah dari bagaimana kita memanfaatkan material ini menjadi bagaimana cara kita menemukan material baru dengan karakter yang lebih baik dari material yang telah ada. This is where materials and metallurgical engineers work. Kami merekayasa material. Program Studi Teknik Material dan Metalurgi Institut Teknologi Kalimantan atau ITK telah terus meningkatkan kegiatan pembelajaran sains dan teknologi untuk rekayasa material sejak tahun 2013. Berdiri di bumi etam Kalimantan yang berlimpah potensi dan kekayaan sumber daya alam, program studi Teknik Material dan Metalurgi ITK terus berkembang untuk menciptakan terobosan-terobosan rekayasa material. Telah mendapatkan akreditasi B oleh BAN PT, program studi Teknik Material dan Metalurgi ITK selalu berusaha agar semakin baik dari masa ke masa. Program studi ini memiliki visi untuk menghasilkan kompetensi unggul dalam bidang rekayasa material dan metalurgi di wilayah Kalimantan pada tahun 2025. Dalam perjalanannya, program studi Teknik Material dan Metalurgi ITK terus mengembangkan fasilitas penunjang kegiatan belajar mengajar yang lebih baik, termasuk laboratorium yang semakin terdepan dalam menyediakan layanan penelitian dan pengembangan riset. Hingga tahun 2020, terdapat 10 dosen dan 2 staf untuk membantu pembelajaran 300 mahasiswa di program studi ini. Kolaborasi penelitian juga dikembangkan melalui network antar institusi. Program studi Teknik Material dan Metalurgi ITK akan terus berkembang untuk melahirkan sumber daya manusia yang unggul dalam kompetensi bidang rekayasa material dan teknologi bahan, tidak hanya demi kemajuan industri, melainkan juga pengabdian masyarakat yang berkualitas.
Demikian pengenalan program studi Teknik Material dan Metalurgi. Sampai jumpa di pertemuan selanjutnya.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Respectable Director of Institut Teknologi Kalimantan, Profesor Budi Santosa, PhD. Excellencies, the Vice Rector of Academic Affairs of Institut Teknologi Kalimantan, Nurul Widyastuti, SSI, MSI, PhD. Excellencies, the Vice Rector of Non-Academic Affairs of Institut Teknologi Kalimantan, Dr. Muhammad Mashuri, MT. Honorable Speaker and one of Program Directors of Sakura Science Program at Saga University, Professor Dr. Masato Tominaga. Honorable Invited Speakers, Kartika Anoraga, SSI, MSI from Institut Teknologi 10 November. Unita Triana SSI MSI from Keio University, and Dr. Gothaman Krishnan from Monash University.
Anda pakai apa itu? Zoom. Punya Bapak.
All
Iya.
of the invited guests from the official of Institute Teknologi Kalimantan, researchers, college, and students from various institutions, ladies and gentlemen, welcome to the second international webinar series in collaboration with Sakura Science Alumni, with the theme of Young Researchers on Material Science and Engineering. My name is Saima Rindasari, and I will act in today's webinar. I got my bachelor degree from Institute Teknologi Kalimantan before continuing my magister and doctoral at Saga University, Japan. I'm also an alumni of Sakura Science Program from 2018. Now, on behalf of collaboration between Department of Materials and Metallurgical Engineering of Institute Teknologi Kalimantan and Saga University, I would like to extend a very warm welcome to all of you. We appreciate you for taking the time of your busy schedule to join us today. Before we come to the main session, let me deliver the structure of today's webinar as follows. 1. Opening. 2. Sing the national anthem of Indonesia, Indonesia Raya. 3. Opening remarks from Rector of Institute Teknologi Kalimantan, Professor Budi Santosa, PhD. 4. Speech from Professor Dr. Masato Tominaga as the Program Director of Sakura Science Program at Saga University. 5. General lectures from invited speakers and discussion session. 6. Closing. Before we move to the main agenda, let us sing and listen together to the national anthem of Indonesia, Indonesia Raya. First of all, I would like to introduce both universities involved in the preparation of this webinar. First one is Institute Teknologi Kalimantan, especially Department of Materials and Metallurgical Engineering. Institute Teknologi Kalimantan has established since 2014. In 2020, there are 17 departments with 145 lectures and 5,089 students. Institut Teknologi Kalimantan is located in Balikpapan, East Kalimantan, Borneo Island, Indonesia. The campus also already received an official accreditation with B accreditation. One of the 17 departments in ITK, Materials and Metallurgical Engineering, become one of the emerging departments that always eager to develop. They also got B for national accreditation, which make them desire to improve into the better place for study. Materials and material engineering is an interdisciplinary field that learns about how to design materials for creating functional products. In 2020, the department has 10 lecturers with various research interests such as welding, corrosion behavior and prevention, nanomaterial and porous material, biomaterial, polymer and composite, as well as modeling and simulation. Also, there are around 400 students in total. In 2020, Department of Materials and Metallurgical Engineering, Institute Teknologi Kalimantan, and Faculty of Science and Engineering Saga University have signed joint collaboration agreement. Next, I would like to introduce about Saga University. Saga University is a national university located in Saga Prefecture, Japan. Saga Prefecture is located next to Fukuoka Prefecture, where Fukuoka, the largest city in Kyushu Island, is located. Saga University was first established in 1949 from the pre-World War II Saga High School, Saga Teaching College, and Saga Youth Teaching College. Then, Saga Medical University set up in 1976 as the only national medical college in the prefecture, was integrated into Saga University in 2003. As for 2020, the number of students is around 6,600, including undergraduate program for about 5,800 students and graduate students of 800 students. From its three main campuses, Honjo, Nabeshima, and Arita, Saga University now has 6 faculties: education, economics, science and engineering, agriculture, medical, also art and regional design. In Imari, Institute of Ocean Energy of Saga University, or IOES, is located. And now, to formally kick off our event, it's my pleasure to invite the Rector of Institute Teknologi, Professor Budi Santosa, PhD, to deliver an opening remark. Please welcome. I'm sorry, Professor Budi. Maybe your voice is muted.
Okay.
Thank you. Thank you.
Thank you. I'm sorry. Yeah. Good afternoon, everybody. Welcome to this seminar, International Webinar Series 2, Young Scientists on Material Science and Engineering. The Honorable Professor Dr. Masato Tominaga as a Sakura Sen Program Director, and then the Honorable Speakers Kartika Anuraga from ITS, and then Junita Triana from Keio University, then Gautaman Krishnan from Monash University. Thank you for being the speaker for this webinar. And also, thank you for the all audience for this coming to this webinar. Yeah, I appreciate this activity among the pandemic, coronavirus pandemic. We can still make this academic activity, which is very important for us as a academician, for us as students, and for us as a lecturers. by doing this activity, we hope that the spread of knowledge of science is not stopped, so we can still spread the beneficial knowledge, especially in the field of material science and engineering, also metallurgy. This is the second webinar series in the same agenda. So we hope that next year we can still make the same activity with more many people. And then if the pandemic is already gone, then we can make this offline. So we can meet each other face by face. From this activity, we hope that our cooperation, especially between Saga University and ITK, can more tight. We can make other program which is beneficial for us in terms of developing cooperation in terms of research or making seminars or other scientific activities. Okay. By saying Bismillahirrahmanirrahim in the name of God, I open this international webinar series to young scientists on material science and engineering formally. We hope that this activity will be work with no constraint fluently, and then give benefit for all the participants. And again, I thank you for Professor Dr. Masato Tominaga for this cooperation. Masato Tominaga from Saga University also for these three speakers. Thank you. Good afternoon.
Thank you for your opening remarks, Professor Budi Santosa. And now we'd like to ask to all of the participants to please open your camera. So there are several slides. So we will do one by one. So first slide, in a count of 3. 1, 2, 3. And then next slide. 1, 2, 3. Also next one. 2, 3. So please give your best smile. So 1, 2, 3. Maybe for last one. So 1, 2, 3. Thank you for your cooperation. So next agenda is remarks, which will be delivered by Professor Dr. Masato Tominaga as one of Program Director of Sakura Science Program at Saga University. Please welcome.
Okay. Okay, can you see my slide?
Yes.
Okay, thank you very much. Thank you so much, MC, Ms. Shaimalinda Sari, for your kind introduction. My name is Masato Tominaga. So good afternoon, ladies and gentlemen, thank you so much for your attention. Thank you so much for your participate in this meeting. So I would like to introduce Saga University briefly and introduce Sakura Science Program. And then, first of all, I would like to give my great thanks to Rector of ITK, Professor Budi Santosa, and also Department Head of Material and Metallurgical Engineering, Mr. Jatomoko Awari, and all of the lecture of Department of Material and Metallurgical Engineering and volunteer student. Thank you so much. And also, I would like to give my special thanks to Gusti Tajara Sensei for her best effort to realize this webinar. Thank you so much. So, and also, it is great honor to be here as a keynote speaker of this webinar. And then I'm very happy, very happy because my student will present of their research. I understand they are not my real student, but I believe they are my student in my Japanese side. I'm a supervisor all of alumni of Sakura Science in Japan side. So 3 years ago, I had a meeting, alumni of Sakura Science. We had a dinner each year in Surabaya. So yes, she is today's speaker, one of the speaker, Yunita Sensei. Also, she is the Karutika-san, also today's speaker. I had a great time 3 years ago, face to face. And today, I have a dream to realize international meeting with alumni of Sakura Science Program. So I'm so happy today. Thank you so much for, Rara Sensei and all of the staff of department staff. Okay, I would like to introduce my university briefly. Department of Education, Department of Design, Department of Economy, Medical School, Department of Science and Engineering, finally, Department of Agriculture. Okay, I stop it. Thank you very much. Already, this Shaimarinda Sari informed place of Saga. Saga is located in south part of Japan. So Saga city is located in local side. So if you like nature, if you like quiet, please visit Saga University when you have a chance to visit Japan. Okay, and then I move to introduction of Sakura Science program. Maybe my talk introduction would be not enough for you. So if you are interested in Sakura Science program, also you can check the this homepage. This is the QR code here. Okay, this is the video of Sakura Science program produced by JST.
Connecting foreign youth in Japan to nourish future global science leaders. Sakura Science Program. Have you heard of it? Japan Science and Technology Agency, or JST, launched Sakura Science Program in 2014. The program invites outstanding youth from other countries for a short period to Japan to observe Japan's cutting-edge science and technology. Sakura Science Program encourages foreign youth to mingle with Japanese researchers and students to expand their personal and research network globally. Most of the people in charge at receiving organizations say Sakura Science Program accelerated their globalization. Now, let's take a look at the Sakura Science Open Application Program. Foreign and Japanese organizations make an exchange program in science and technology field together. After the selection by the committee members, JST provides the selected programs with financial support. Eligible persons are outstanding young people, 40 years and younger, with a nationality other than Japan. Exchange programs have been implemented at educational and research organizations and others throughout Japan. In the survey of participants in 2019, most participants answered that they had a more positive view of Japan than before and were impressed by Japan's state-of-the-art research facilities. Sakura Science improves participants' understanding and impression of Japan. The number of participants in Sakura Science program increases every year, and more Japanese organizations will join Sakura Science from now on all over Japan. Sakura Science Club, a club for alumni of Sakura Science program, offers many resources to enhance further international exchange among members. The club's website is a trove of information on life in Japan and how to engage in study abroad activities in Japan. Through its alumni meeting, the club widens the circle of exchange even after participation in the program. Members who visited Japan through Sakura Science program and decided to study in Japan typically find living in Japan an exciting experience. Sakura Science program has received support from Nobel laureates and many ambassadors of foreign countries to Japan.
Maraming salamat Kanazawa University. Maraming salamat Sakura Science Project.
Would you like to come to Japan to experience cutting-edge science and technology?
Okay, thank you very much. Again, this Sakura Science started from 2014 by JST, Japan Science and Technology Agency. We call JST. And then last 6 years, 33,000 people visited Japan. So main aims, there are three main aims. First one is support the development of talent human resource from overseas who have the potential to contribute to innovation in science and technology, and support continuous interaction between Japan and other countries and the region. Second one is promote globalization of Japanese educational and research institutes. Third one is strength good relationship between Japan and other countries and the region. I skip this one. So this is the ratio of visitor from 2014 to 2019. So from China, Chinese 32%. Next, Thailand. Third, India, and fourth, Indonesia. And then this program started from 2014. At the time, visitor number was around 3,000. And the number is increasing every year and almost reached to plateau at around the 7,000. Of course, as you know, last year this program was stopped by COVID. And then this is the data of 2019. Around 2,000 people visited Japan from East Asia, and 2,700 people visited Japan from Southeast Asia, and around 700 from Southeast Asia. This is I picked up the data of Indonesia. So Sakura Science program has three types of program. So one is Science and Technology Experience course. This is short course because it is limited to 7 days. So B course is collaborative research activity course. It's limited to 3 weeks. And then C, Science and the Technology Training course. The period is limited to 10 days. So this is the course A, B, C. So many visitors attend to the course A, mainly course A. So course B and course B is limited. And visitors almost from university student of bachelor and graduate student. And there are some faculty members. A total number was around 600 people at 2019. So I would like to show you the step to realize the Sakura Science program. There are 4 sites. For example, a university in Indonesia, for example, Unita Sensei of ITK, the program director like me, and the Saga University side, and the JST side. Okay. At first, JST informed us about public offering. And then program director made program with counterpart. For example, Unita Sensei. I contact her personally and I did a negotiation with her. So we discussed about how many teachers, how many students, so how long period, when we can start. And then At this point, very important point is strong relationship of trust. This is important and this is necessary. And then I submitted the application to JST. And then if we have a lucky, I have a information of acceptance from JST. To fix program, I discussed with Unita Sensei again. And then we decide invited persons and period. And then I submitted the final program to JST. And then I collect the personal information from Unita Sensei to JST for supporting, taking up, for support the visa. And then I registered the airplane, guest house, and I did many documentations with university staffs. Also, I informed the counterpart this information. And then I did the program. Finally, I informed the financial report to JST. So like this process. The important point is the strong relationship of trust with the counterpart. Okay, so this is the real print screen. This is all of the documents I prepared last time. So it takes much time to do program, to prepare a program, everything. So many Japanese professors don't like to do this program, because, it takes a time and also 100% volunteer. So, but some Japanese professors like to do Sakura science program, like me. And then program director make a program. So it means the program strongly depends on the program director. So why? There are some important points required to be accepted. For example, first is, why is it Saga University? So why Saga University? So second, does studying at Saga University have the strength of Japanese research? Third, is the program attractive? Is it a program that you would like to visit Japan again? Fourth, is it an institution with excellent invitees? Can you expect continuous exchanges? Yeah. So we need to think about this one. So this one depends on the university, depends on the program director. So program depends on the director, depends on the university. So I would like to introduce why ITK Saga University made the strongest relationship. So there is some history. The history started from 2013. So my first visiting Indonesia was 2013 in November. So this is me. Looks like very young. He's a professor of chemistry department, Professor Fansri. And you can see today's two speakers in in photo. So she is the Unita Sensei, today's speaker, and also she is the Miss Kartika-san, today's speaker. Yes. And then after visiting Indonesia, I like Indonesia. I visited Indonesia every year. And then also I have a very nice friend in ITS. For example, Professor Freddy and Dr. Dharmawan. So Dr. Dharmawan was a student of my previous university. So he finished the doctor degree and he went back to ITS. So I'm very happy to meet him in Indonesia. So I visited Indonesia every year. And then, so in 2016, suddenly I had an email from Unita Sensei. Sensei means teacher in Japanese. So I use Sensei. So I had an email from Unita Sensei. I did not remember her. So sorry, because at the time she was one of the students. So I did not remember her name. But I knew she was a student of Dr. Freddy, Professor Freddy. So as I decided to invite her to my laboratory by Sakura Science program. This is a real email, and this is a photo of Sakura Science program at the time. And then our relationship continued until 2020, and I made the MOU before COVID. So January before COVID, we are very lucky. So I visited ITK. My dean also visited ITK, and we had a signature ceremony in the ITK campus. It was very nice. This is all of alumni of Sakura Science program who visited my laboratory. So important point is key person in the counterpart. For example, in the ITS, so Professor Freddy and Dr. Dharmawan, they are a key person for me. So, on the in the ITK side, Unita Sensei and Kustira Sensei, they are key person for me. So I invited now 23 persons. But now I need to stop because of COVID, but I will continue this program. And maybe next you. So if you are interested in Sakura Science program and you want to attend the Sakura Science program, you find the key person in your university who has a strong relationship with Japanese professor. And then you contact the key person and inform the person. For the ITK student, please contact Unita Sensei or Rara Sensei. ITS student, please contact Professor Freddy or Dr. Dharmawan. Unsuri student, please contact Dr. Lady Sensei. Universitas Bunhata student, please contact Lenny Sensei. And Indian student, please contact Professor John. So, Linda, I have a time. Okay. So I would like to show our picture briefly. So this is photo of 2015. This is first time Sakura Science program for me. At the time, I invited Dr. Gotaman, today's presenter, speaker from India, Ganjigram Rural Institute. She is the Kisubeya-san. We had a party also. Yeah, Dr. Gotaman did experiments, research. He did sightseeing and visit to another city by using Shinkansen, bullet train. And the 2016, we had one visitor from ITS. She is Chanifa-san, Ifa-san. She will join to my laboratory from October as a master course student by Japanese government scholarship. And then this is 2017, Sindhu-san from Ganji Rural Institute, Aldi-san from ITS, chemistry department. At the 2018, I had 3 visitors from ITK, sorry. Unita Sensei and Mr. Sopian and Linda. She is today's MC, and she is my student of doctor course. She finished a master degree last September, and she continued her research as a doctor course student. And she has a Japanese government fellowship. Yes, enjoyed. We had a party. Of course, did experiments, synthesize carbon nanotube, and like this. And then in the August, we have 3 visitors from India, Mr. Aru from India, and Ricky-san and Faris-san from chemical engineering department of ITS. And then December, Kartika-san visited my laboratory, and Ricky-san also visited my laboratory from ITS. Hendrik-san and Titin-san visited from ITK. At the time, we had a visitor from Gajah University, Utami-san. He stayed in my laboratory for 3 months. Yes. Yeah, we did the sightseeing. Okay. Oh, I love this photo, very nice. Yes. 2019, I had a visitor from Unsuri, Ria Sensei, and Fiji Sensei from Unsuri, and he's Yuda-san from ITK, and ITS, and Firman-san from ITS. And last year, before COVID, Gusti Sensei, Rara Sensei visited my laboratory, and Ansta-san also visited my laboratory from ITK, and Rivaldo-san visited my laboratory from ITS. Pam-san from Chulalongkorn University. Okay, thank you very much. I prepared the my homepage in Bahasa Indonesia, so you can use this QR code. And thank you so much. Terima kasih for your kind attention. Thank you very much. Linda, finish.
Thank you very much for Professor Dr. Masato Tominaga for your speech and explanation about Saga University, also Sakura Science Program. I'm sure the participants today will understand, especially about Sakura Science Program. What is Sakura Science Program? So maybe because of the time, I would like to just skip the question and answer. And then if I could conclude from his talks before, so Sakura Science Program is a fully supported program by JST, and the key to this program is strong relationship between the program director who opened this program and your supervisor, your lecturers in your university. So the students from ITK, ITS, UNSRI, and all of the university, Professor Tominaga already said, maybe you have the chance next to join Sakura Science Program. And then I would like to also mention that all of key person in today's webinar, including me, the MC, moderator, also all three speakers are alumni of Sakura Science Program during, under Professor Tominaga supervision. And then he took a lot of effort, a lot of his time for the Sakura Science Program at Saga University. So all of us feel really privileged, especially for me now, I can continue my study here in Saga University. Thank you once again, Professor Masato Tominaga. And then next, to provide comfortable situation during webinar, we kindly deliver you some information regarding the rules of today's event. The first, so participants are required to change the name during the webinar with the exact name and institution as on your registration form. The format is your name underscore your institution. So for example, Hanifa Nur Eldiana underscore Institut Teknologi Kalimantan. Second, participants are expected to turn on the camera and mute the voice during the webinar unless discussion session. The third, participants are expected to use a virtual background that can be downloaded in this link, so intip.in/virtualbackgroundmme webinar. The fourth, participants are allowed to ask questions via chat at the Zoom meeting by sending questions privately to the moderator or using the raise hand feature. And last one, the e-certificate will be given to the participant who fill out an attendance that will be shared at the end of the event. So without further ado, I will invite the moderator of today who will lead the speech and discussion session. So today's moderator is Gusti Umindya Nurtajala STMT. So currently she is a lecturer at Materials and Metallurgical Engineering Institute Teknologi. She finished her Institute Teknologi 10 November and then continuing her master's degree at Institut Teknologi Bandung before now become lecturer. And her research field is mainly in nanomaterials and also biomaterials. So please welcome Gusti Umindya Nurtajala STMT.
Okay, thank you, Saima, for your humble introduction. Hello, everyone. I am Gusti Umindya Nurtajala. We lead the speech session for today's webinar. Hope you are in a good condition, in a good health. Nice to meet you all. Actually, I'm fully excited right now to meet the speakers, not only because we are connected in Sakura Science program, but also they are young, like our theme today, young researchers. Maybe some of you have a lot of questions like in your head, how a youth like us can contribute to development in nowadays technologies. Because you know, technologies always get improved day by day, time by time, year by year, especially for today's topic, the development of electrode materials to enhance the sensitivity for detecting maybe blood glucose level in the human body, CO gas level, which is toxic for a human, or heavy metals in environmental pollutants. We have time to discuss it today. So first of all, I would like to introduce you to the first speaker. Okay, she is Kartika Noragama Durani. She is a PhD candidate at Institut Teknologi 10 November Indonesia in Chemistry Department, Faculty of Science and Data Analytics, ITS. She also graduated for her bachelor and master degree from Institut Teknologi 10 November. She had a research interest in analytical chemistry, electrochemical, corrosion, and sensor. She also got dissertation scholarship from Indonesia Endowment Fund of Education, and also in 2018, she also got Sakura Science Exchange Program on Saga University, Japan. Without further ado, please welcome Kartika Anoraga.
Okay, thank you so much. Can you hear my voice?
Sure, yes.
Thank
Clear.
you. Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you for the time and the honorable for Rector of ITK, the honor, the head of Material and Metallurgical Engineering Department ITK, the honor Professor Masato Tominaga as Director of Sakura Science Program at Saga University, the honor all invited speakers. Ladies and gentlemen, good afternoon, and it is nice to see you all in here today. I hope all of you is always in health. And first of all, I would like to say thank you to ITK for inviting me today, and it's an honor for me to be able to attend and share a bit of my experience in this forum. Next, please. Next. Okay, my name is Kartika Anoraga Madurani, and I am an alumni of Sakura Science Program in 2018, and now I am a PhD candidate in Chemistry Department, Institut Teknologi 10 November, or ITS, Indonesia. And during this time, I have several publications in chemo and biosensor, electrochemical, corrosion, and also analytical chemistry. Next. This is my country, Indonesia, and the location of ITS is in East Java, Surabaya City. You can see that this is the landmark of Surabaya City, and the right one is my beloved campus, because I am alumni from bachelor until now from ITS. And also ITS will known as a University of Heroes. So if you come to Indonesia, please welcome to my campus and my city. Thank you. And next. Next, please. Okay, today I would like to present one of our research about nanobiosensor, and you can see this is the progress of nanobiosensor, and it were developed in around 2000. And so what is nanobiosensor? Next, please. Actually, nanobiosensor is a device that can detect the material or organic compound, and this device is coupled with the nanomaterials. And nanomaterials, it means that the material with size in 1 nanometer until 100 nanometers. Next. Okay, and in our department, we are use an electrochemical nanobiosensor. We are developed about it because it is fast, simple, low cost, had a good sensitivity, good selectivity, and it just need a small amount of sample. And this principle of electrochemical nanobiosensor is on the redox reaction of the organic compound that our target. Next. Next, please. Okay. This is our team. Oh, sorry, the previous one. Okay, thank you. This is our team, and we are from Laboratory of Instrumentation and Analytical Science under supervision of Professor Freddy Kurniawan, and behind him is all of the students, and it is from bachelor degree until the doctoral degree. And we are develop several nanomaterial like a nano gold, nano silver, nano zinc, nano nickel, nano tin, and of course nano carbon. In this time, I would like to say more about nano carbon. Next. Okay, you can see that carbon. Why we choose a carbon? Because it is easy to found in around us, and if you want to make a good sensor, you should have a characterize like have a small size, large surface area, and have an excellent electron transfer. So it is important thing to make a electrochemical sensor. So we choose a single wall carbon nanotube in here, and we have a collaboration with Saga University. Next. This is our collaboration research, and from this program, in Sakura Science program, we can make some how to say, make some research in Tominaga Sensei laboratory, and we are synthesize and characterize the single wall carbon nanotube in Saga University. After that, we apply this biosensor for medical purposes in the ITS. Next, please. And from this program, we have actually two publication about electrochemical sensor based on single wall carbon nanotube. You can search our publication, and now I want to show you one of them in for uric acid detection. Next, please. Okay. As we know that uric acid is one of the important organic compound in the medical field. It is because it is easy to know in our body, and you should know the level of the uric acid. If you have a higher level of uric acid, maybe you can get several disease, and we don't want to get that disease. So you should to detect it. So why we are develop the electrochemical sensor? It is the purpose like we want to know the level of uric acid in our body, and then when we are detect uric acid, actually dopamine is interference this measurement. So we want to develop the sensor that can detect uric acid and dopamine in the same times. And dopamine, as you know, if in here in also in chemistry department or in chemistry also chemistry student, and you know that dopamine is related to the happiness in the human, and if so please make your dopamine in your body is stable, because if you have it in a low level, maybe you have you easily to get stress, and in this pandemic situation maybe you can attack you can infected by the virus like that. So please keep happy, please keep happy, and we are hope all of us is always in health. Next. Okay, this is the gold electrode that we are modified with single wall carbon nanotube. No, the previous one please. Okay, and the sensor is only in the surface of the gold electrode that modified with single wall carbon nanotube. If we are synthesize something, we should know that it is successful or not. So we are characterized with a CEM and TEM in Saga University, and also by Raman spectrophotometry. Okay, and you can see that the morphology of the surface of the gold electrode is already in nanomaterial, and the form is showed is single wall carbon nanotube. And from Raman spectroscopy, we have a G-band, and it's indicate that the single wall carbon nanotube is successful synthesized. Okay, next. And this is the performance of the sensor. We are doing it in ITS, and you can see that in the red one is a dopamine, and the blue one is uric acid. So it means that our sensor can detect actually for uric acid and dopamine in the real time, in the same time. So until now we are develop it, and it's just the first research of this sensor. Next. And this is the comparison performance for several electrodes, and the limit of detection is very low in our work. So it means our sensor is work well to uric acid. Next. Okay, I think that's all about the research, and this is a memorable moment of Sakura Science Program. Next, please. Okay, I am so happy because I can be a part of this program, and there is a lot of experience in here, and I never expected that I can go to Japan that time. And actually Sakura Science Program is not only give me the experience in laboratory, but I can meet someone else from the other country. I can share everything with them, and I can learn about the culture, especially in Japan. And also one of the interesting thing, I think, that not all students have this opportunity is when I got experience from Professor Masashi Uno, and I can learn about Raman spectroscopy directly from him. That was so wow, amazing. So this is the picture when I was in Saga University for doing a Sakura Science Program. Next, please. And also we have some moments in Surabaya and ITS when Professor Masato Tominaga came to our country. Next, please. We are going to Zoo Surabaya Zoo, and also we take a picture in the front of the landmark of Surabaya city, and after that we are have lunch in the one of the most famous food in East Java. It is fried duck, and it's so delicious. So when you come to Indonesia, especially in Surabaya, you can try it, and it's just maybe 30 minutes from ITS or maybe less, so it's near, and you just throw by the Suramadu bridge, and you can take this delicious food, I think. Okay, next please. And it's also a memorable moment in our department, chemistry department, and Professor Tominaga is also become my examiner for my dissertation. So thank you so much, Sensei, and we will continue to my next examination. I hope it will be held as soon as possible. Okay, next. Okay, the last but not least, I want to show you about the profile video of my department, chemistry department ITS. So please enjoy it.
Welcome to the Chemistry Department, Faculty of Science and Data Analytics, Institut Teknologi 10 November, Surabaya. The Chemistry Department of ITS was founded in 1970. There are 2 study programs, undergraduate and postgraduate programs covering master's and doctoral degrees. The Chemistry Department has a reputation at the national and international levels. The National Accreditation Unit for Higher Education assigns the accreditation score of A, or the highest in all its study program from undergraduate to doctoral degrees. The Chemistry Department of ITS undergraduate study program ranks the first chemistry study program in Indonesia based on Sinta data. Furthermore, the chemistry undergraduate program has received international accreditation from the Asian University Network, AUNKIA, proving that this study program is equal in the Asian region. The chemistry department of ITS has 6 laboratories, consisting of 1 educational laboratory and 5 research laboratories that can support a wide range of student research and learning activities. The educational laboratory is the fundamental chemistry laboratory, supporting the chemistry department's teaching and learning education process. All classical practicum facilities in the chemistry department are provided by this laboratory. Besides, the other 5 laboratories are research laboratories, consisting of the Instrumentation and Analytical Science Laboratory, the Microorganism Chemistry Laboratory, the Molecular Geochemistry Laboratory, the Natural and Synthesis Chemistry Laboratory, and the Materials and Energy Chemistry Laboratory. These laboratories focus on research and the implementation of the study, including the final projects such as thesis, dissertations, and several collaborative research at the national and international level. The
The laboratories of the chemistry department have been certified lab-based education by LTPM ICS and are equipped with sophisticated laboratory instruments to produce research that has significant impact on the development of science and technology. Not a few chemistry lecturers are also actively collaborating with various industries. The other room facilities owned by the chemistry department include lecture or teaching rooms, meeting rooms, and some spaces with complete facilities for students and the academic community to support the learning process. The chemistry department also provides an equipped and comfortable library, the chemistry reading room, with various library collections to support the teaching and learning process. Students can access books and different current research related to national and international journals with a vast chemical research field.
Thank you. That's all my presentation today. Thank you for your kind attention. I do apologize for my every single mistake. And last I said, wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Kartika Noragat, for presenting your presentation. So, is everyone have question for Kartika Noraga? Please, you could raise your hand or chat in the chat box. Okay, let me give you a brief explanation about her research, which is about nanobiosensor, single wall carbon based actually, to detect dopamine. Is it sufficient or not? Because dopamine give you happiness, actually, yeah? Give you a happiness or lower your stress actually. So this is so important for your mental health right now, because this is a pandemic, it's stressful, I know. So if everyone has question, please raise your hand or fill in the chat box. Okay, we have one question in the chat box. Let me read it from Fikan Mubarak. Why are we using certain type of carbon nanostructure form like single walled nanotubes, not the other type? Is there any special characteristic for each carbon nanostructure?
Okay, thank you for the question. Who is the name? Sorry. Who is the hello? Fikan.
Yes.
Fikan. Okay. Thank you for Fikan. Thank you for the question. It's a good question, I think. Why we choose a single carbon nanotube? Because it's have a a good characteristic for a sensor, and it depend on our organic compound target, I think. And as far as I know, if we want to specific or and if a good sensitivity and also good selectivity, we should use a good material, and one of them is single wall carbon nanotube. And this material has a specific characteristic like a small size. We can make it in nano size, nano material, and then it is also have a large surface area, and it's very important because when you said about sensor, it's mean that the interaction between the surface area and the organic compound target is very, very important. So we use it because it has a large surface area, so it can easy to us to detect the organic compound like that. And The special things one also, it has an excellent electronic transfer. In electrochemical, it is based on the redox reaction. So if you have a material that has excellent electronic transfer, you can make it to detect the organic compound that your target. I hope it can answer your question. Thank you.
Okay, thank you. It's I think it's very clear. So, okay, I have one more question from the chat box. Maybe this is the last question from Nihayatur Rohma. May I ask you a question a bit out of topic? Can we develop nanomaterials as biosensor to detect COVID-19 mutation? Can you please describe it briefly? Okay, it's interesting, I think.
Yeah, it's very interesting because we are now in a pandemic situation, right? Actually, um, before my dissertation is about carbon nanotube, about the carbon material, but now because of pandemic, I changed my research, and it is connected with COVID-19, but with different method. So if you ask me about it is possible or not, I think it's possible because there are a lot of research that published about COVID-19. It also used a nanomaterial supporting to detect COVID-19. I think that's my answer. I hope it's clear for you. Thank you for the question, Nihayatur Rohma.
Okay, so it's possible. There's nothing impossible in this world, okay? Okay, thank you, Kartika Noraga, for your explanation, for your presentation. Hope you have a great PhD moment. Hope you can pass it very well. Okay, let's continue to the second speaker. We have a young lecturer also. She is my beloved colleague. She is Yunita Triana, SSI MSI. She is right now is a PhD candidate from Keio University, Japan. She is also lecturer of Materials and Metallurgical Engineering Institute Teknologi Kalimantan. She has her bachelor degree from Universitas Mula Warman and continued her study at Institut Teknologi 10 November. She has research interest in analytical chemistry, biosensor and sensor, electrochemistry, and corrosion. And she has also got a lot of grants from LPDP scholarship, also Budi LN LPDP scholarship. And then she got also research funding for young lecturer from Ministry Research Technology and Higher Education Indonesia, and also ASEA Uninet research funding. Okay, so here is CS, the second speaker, Yunita Triana.
Okay, thank you very much. Okay. Anybody can hear my voice?
Sure, it's very clear.
Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon, everyone. Your Honorable Director of ITK, Professor Budi Santosa, Professor Masato Tominaga, good afternoon, and also Professor Freddy, and the Head of Material and Metallurgical Engineering Department, Mr. Jatmoko Awali, and all the committee, my friends, lecturers, and also all the speakers and the audience from Indonesia and outside Indonesia. Good afternoon, everybody. I hope that you are well now among the COVID-19 issue. So I hope that we are healthy. And thank you for the chance for giving me time to speech and discussion today about my work in Japan and also my experience when I joined a Sakura Science program. before, I would like to share my screen. Can anybody see my PPT?
Yep.
This is my sharing session today in the second international webinar in collaboration with Sakura Science Alumni. And I'm so excited. I'm so honored that Tominaga Sensei said to me that ITK and Saga University had strong relationship of trust. That I'm very happy to hear that. And my topic today is about the application of boron doped diamond electrodes for gas sensors. So today we would like to discuss about diamond. What is diamond? How to fabricate it? Before, I would like to introduce myself. This is the presentation's time order because the committee gave me 20 minutes and also question and answer 10 minutes. So only 2 minutes for self-introductions and the explanation about BDD electrodes, fabrication, and H2S sensor is about 13 minutes. And the experience of Sakura Science program about 5 minutes. And we can discuss more question and answer about 10 minutes. And this is my photo if you cannot see my reel in offline. And my complete name is Yunita Triana. You can call me Nita. I'm 23 years old and I have been married. I'm from Indonesia. My career now is I'm lecturer at Department of Material and Metallurgical Engineering ITK. Sorry. Okay, and this is my awards and organization. So Lala Sensei already told you about my awards, and this is the organization that I joined, the science and technology organization like Himpunan Kimia Indonesia, Organization Women Science, and also Ikatan Ilmuwan Indonesia International, and Badan Kerjasama Pendidikan Metalurgi dan Material, and also Electrochemistry Society, and also ACS. So if we meet in this organization, please send me a message that we already meet but in online webinar. Okay, and this is my university. Keio University. Keio University has 6 campus, and I am in a Yagami campus. This is my picture of my university, my campus, and the location is 1.4 kilometers from Hyoshi stations, and this is the address. And as you know that Keio University already was built on 1858 year. And we have 6 campus in the metropolitan area, and one of the campus is Yagami. Yagami is in Yokohama, and one of the center of campus is Mita campus, that's in Tokyo, and we have 33,400 students, and from 73 countries in the world. And based on the 2021 KS World University ranking, Keio University is in the 191st rank. So it is not a bad ranking in the world. And this is my academic and non-academic activity in Japan, and I'm now a PhD student D3. So now I'm in the 3rd year under Professor Dr. Yasuaki Einaga Group Research from 2019 until now, and I got supported by BUDL and LPDP Scholarship Indonesia Government. So this is my group research, and this is my supervisor. And about non-academic, now I take before COVID and also in this COVID with the very careful treatment that I go to traveling like in Yokohama, Tokyo, Saitama, Osaka, Kobe, and Kyoto. So I like to take a picture of them, photography, and make a video of my journey to be a memorable time in Japan. And also I study about the culture and Japanese language. So this for example, this photo, I study about the tea ceremony. Tea ceremony usually for New Year. Every New Year, Japanese have tea ceremony for the family and friends. And this is my education and research background. That in my bachelor, I'm from Mula Warman University Samarinda, Indonesia, under Professor Dr. Aman Sentosa Panggabean, and in department chemistry. At that time, my thesis is pre-concentration of trace elements, so it is about the analytical chemistry. And I continue my master in Institut Teknologi 10 November under Professor Dr. Freddy Kurniawan, and my topic research at that time is urea sensor by using PT modified electrode. So from this laboratory, I really interested in the electrode materials. Then because I really interested in the electrode, so I continue my PhD in Japan and under Professor Dr. Yasuke Inaga. And my topic now in this lab is gas sensor by using boron doped diamond electrodes. And this is my focus research. So many topic in my laboratory. We have 3 big laboratories, and such as like CO2 reductions and degradation of organic materials by BDD. And I focus on the sensor, specifically is gas detection. And for this laboratory, I already published 2 papers, and the first is hydrogen sulfide, and the second is nitrogen dioxide. Now I'm focused on the biomedical applications, gas in the body, gas in the human body, in my current experiment now. And I would like to talk about my first paper today about hydrogen sulfide sensor. And okay, first of all, before I explain about the paper, I see the participants, most of the participants are students. So I would like to talk to you about how to fabricate of boron doped diamond material or electrodes in my laboratory. And based on this paper, this is my supervisor, Professor Yasuke Inaga. He developed electrochemical application by boron doped diamond, and the fabrication is also published in this paper. So first of all, I would like to explain to all of you that what is diamond. We know that diamond is like for jewelry, right? Diamond is a solid form of carbon which has 3 dimensional shape. Each carbon atom attached with 4 other carbon atoms via covalent chemical bonding. So this is the anybody hear my voice well? Because I hear sounds from others. Okay, so this is the difference between carbon and diamond. So the parameter is like, what is the definition of carbon? What is the definition of diamond? What is the category? What is the appearance? What is the hardness? Okay, the appearance in carbon, we can see visually that carbon has a dark color. And diamond typically yellow, brown, or gray to colorless. And also the hardness, the carbon is not so hard as diamond. So the diamond is #1 hard material in the world. So this is the picture, like this is graphene. This is one of the kind of carbon, like Kartika Sensei explained to you, the previous speaker. And this is the structure of diamond. But in our laboratory, we dope boron inside the diamond. So how to make it? So this is the way we use microwave plasma assisted chemical vapor deposition, or the name is MPCVD. So we have two big machines to make the boron dope diamond. And this is the condition, like the substrates is silicon and the material is silicon and boron. The source for the source of boron, we use this material, and some condition that we make the preparation. So this is the scheme of how to make the BDD. So this is the substrates, this is the silicon, and BDD will grow. You can see in the next picture, BDD will grow in front of up to the growth substrate. So you can see you can study and know about the typical of BDD from this paper. This is a good paper. So McPherson is one of the women who focus on the boron dope diamond. So the picture is like this. And this is the characterization of BDD electrode. So after I made BDD, usually we see the appearance by same image. So the purpose is we would like to see the size. So if we got the similar size, it's usually good, but not of same image only. We also take the Raman spectra. So for example, in 1300 is for a diamond structure. So diamond already shape in the structure, and typical spectrum on 500 and 1200 show sp3 carbon and 2 peaks of boron. So 500 here, so this is the boron, and 1200 near here. So if the spectrum we got like this, so usually it is good for sensor, but also we must check the performance by using cyclic voltammetry or electrochemistry. And this is the explanation of the paper. The title is Oxidation Reactions of Dissolved Hydrogen Sulfide Using Boron Dope Diamond. And this is the Q1 paper in the Journal of Electroanalytical Chemistry. So you can open it if you would like to study more about this topic. And first of all, I would like to explain to you why I took an experiment about hydrogen sulfide. This is the historical of hydrogen sulfide. So from 1700 until 1800, so many incident helped by hydrogen sulfide. So this is a many accident, and H2S is confirmed in several system. And also the lethal effect, the researcher already reached on 1803, and 150 years later, many researchers do what is the effect by the concentration. So like 20 until 100 ppm, you will there will be odor, there will be not good smell in under 1 ppm, and 20 and 100, your eyes will be so sick, and also the irritants in these concentrations. So a very important reason to detect this hydrogen sulfide gas. And so many methods to detect hydrogen sulfide. For example, the conventional like methylene blue, colorimetric, and iodometric titrations, and also by using instrument we can use gas chromatography and also high pressure liquid chromatography, and also we can use the fluorescence by electrochemiluminescence and fluorescence. And the popular one is electrochemical. So in the electrochemical, we usually know about direct amperometry and ion selective electrode. So focus on this research is by using electrochemical method, by using cyclic voltammetry. So next is, what is the common electrode to detect H2S? The common electrode is glassy carbon and platinum. Usually in a glassy carbon, H2S has the sulfur falling in the surface of carbon. So they should modify glassy carbon by using polymers. In this paper, they use a modification electrode by using polymers to prevent the sulfur falling. And also in the platinum, sulfur is react with the PT to make PTS. So to prevent this falling in the surface, they use a modification electrode by using room temperature ionic liquid. So RTIL is organic and are very dangerous for environment in this case. And in this research, I will use a boron doped diamond electrode because we believe that BDD is the environment friendly, high durability, and a simple procedure to detect hydrogen sulfide electrode. And this is a paper who show the potential white compare with glassy carbon, gold, and also PT. So BDD has the widest potential window. And what is the BDD strength? BDD strength is like low background currents, extremely wide potential window, like I show you in this red color, and also resistance to falling. So if we remember that, why it should be resistance to falling, because on a glassy carbon and PT, sulfur can be formed when we react the H2S gas. And also, the purpose is study of oxidation mechanism of dissolved H2S by using BDD electrodes, and we will measure the analytical performance. And this is the simple experimental. So I made hydrogen sulfide gas by using a very simple reaction from FeS plus 2HCl, and it is become H2S gas here. So I bubble the gas from this tube to KCl04 0.1 molar. And I detect the signal by using electrochemical measurement, and the concentrations I check by using methylene blue method. So first is H2S bubbling process, and then the electrochemical measurement by cyclic voltammetry, and this is BDD. So BDD as the working electrode, and also methylene blue to confirm the concentration. And the sulfur layer investigation is I used XPS to check the surface of a BDD. Next is, first I check the signal in pH 7. So in electrochemical measurement, we care about pH because pH can give different behavior. So first I check pH 7. In pH 7, I got 3 signal in 0.5, 1.3. So this is broad potential, and also 1.74. And based on this graphic from this paper, that in pH 7, there is 2 product here in pH 7. H2S gas and HS minus in pH 7. And how to confirm the reaction of this signal? So I try in high pH, pH 1.6. In pH 1.6, I only got 1.74. If you remember, in this pH 7, I got 3 oxidation potential, and in this pH 1.6, I got 1.74 only. And based on this graphic, in 1.74 only one species, only H2S gas. So the next investigation is about scan rate dependence. So I made the scan rate dependence to check the electron number. From this step, I got the number of electron is 7. And the number of electron is 7, and the oxidation potential is at 1.7 volt, only one oxidation potential. So dominant fractions at pH 1.6 is H2S species, number of electron is 7 electron, and the oxidation product of H2S is S2O62 minus based on this Pourbaix diagram. So in my hypothesis that the oxidation reaction at 1.7 volt is H2S plus 3H2O, and the product is S2O6 plus 8H plus and via 7 electron. And also I try in the low pH in 10.2. In 10.2, I got 2 potential. In pH 7, I got 3, right? 0.5, 1.3, and 1.7. In pH 1.6, I just got 1.7 here. But in pH 10, I got 2, 0.5, and 1.3. Based on this graphic that in pH 1.2, there is one species, HS minus. And then I also do scan rate dependence. And in this pH 10.2, via this equation, I got this is 4 electron. And then dominant fractions at pH 10.2 is HS minus species. The number of electron is 4 electron. And based on this Pourbaix diagram, in pH 10.2, you can see 10.2 here is the area of S2O32 minus. So my hypothesis is oxidation reaction at 0.5 volt is HS minus plus H2O become S2O32 minus plus 4H plus via 4 electron. And how about the in pH 7 and pH 10? If you remember that I got 1.3 volt here, right? I got 1.3 volt here. What is this? So I try to make some solution. I try to make some solutions, and via this Na2S2O3, I got oxidation near here. So in my hypothesis is this is the oxidation product. The oxidation product from this oxidation. So also the oxidation reaction of OH minus at 1.25 volt is published in our group paper that oxidation signal at 1.3 volt might be an overlapping of the two conditions. So the first condition is the product of this oxidation, and the second reason is this is the OH minus signal, so overlapping. And next, I did
Sunita Sensei, your time is over.
Okay, so sorry, maybe just give me 5 minutes. And this is the comparison of BDD, GC, and PT. So I compare, and this, of course, BDD has good LOD beside GC and PT. Sorry. This is my experience to join Sakura Science program, and this is the facility that you got. So sorry, Tominaga Sensei, I would like to explain this to the students what is the facility. So you will get the ticket airplane Surabaya Fukuoka to Fukuoka Surabaya, and also you got the allowance. So you are free to register the visa, and also you got the health insurance, and also you got money, and also you will sleep and stay in the good guest house Saga University. And okay, Saga University is around here, Kyushu, and now I'm here in Kanto. So I'm near Tokyo. I'm near Tokyo now. I'm in Yokohama. So the Sakura Science Program under Professor Masato Tominaga is in a Kyushu area. So I went to Saga, Fukuoka, and Kumamoto at that time. And in 16 to 25 January, the weather is winter, so 2 until 4 degrees Celsius. So if you join this program, please bring your thick jacket because that's winter. And this is the academic activity. So we fabricate the carbon nanotube electrodes and how to make it, what is the application, and also we study about the non-academic activity. So it like historical place in Saga, tourism place at Kumamoto, and from my impression is Japan is good in waste management, cleanliness, silent and polite, good arrangement, creative and fresh idea, and so on. And this is I talk about future planning between ITK and Saga University when I joined the Sakura Science, because this is the first Sakura Science that we would like to have cooperation between Saga and ITK to have legal MOU. So Tominaga Sensei come to ITK in 2020, and also I talk about student of ITK continue higher education. So Mrs. Tahima today is our program, our result program. So, and next Sakura Science program for ITK. So we close with the cooking Japanese food together, takoyaki and so on. And I got valuable experience about education atmosphere and life in Japan. At the same time, at that time, my intention to continue PhD in Japan was stronger than before. So this is in we met again after Sakura Science in Surabaya on October 17, 2018. And also Tominaga Sensei come to Yokohama and met me in September 7, 2019. And also we met again in online in 2020. So when I met this PPT that, Sensei, we met every year. So this year also we met online. So it is good for our cooperations continue. And okay, thank you for attention. Sorry for the time. And this is hydrangea. So now in Japan is rainy season. So this flower is only bloom in the rainy season. So the name is Ajisai. So I like to take a picture of Ajisai. This is for you all. Thank you very much.
Thank you very much, Yunita Sensei. It's a beautiful like you.
Thank you.
Okay, actually, there's so many questions on my chat box, so please let me read one by one.
Okay.
Okay, this is from. Okay, I'm sorry I couldn't see. Tripaus Hasiholan Hutapea.
Okay.
He has two questions. First, diamond is one of the expensive materials. If we make it in big fabrication, does it cost money? And the second, what do you mean about low background current? Please.
Okay. So, sorry. BDD is, of course, it is expensive, but we don't use BDD so much. So if the surface area maybe only 1 centimeter square, so we don't use many BDD, or we just use the very small surface area in 1 centimeter square around, and then for sensor. And then if we compare the durability, because BDD is a very stable, it's a very strong surface, and the electroactive is a very good, so we can use it for a long time. So for example, I use one BDD like 1 centimeter square for H2S sensor, for NO2 gas sensor. So I don't use different BDD. So just one. So high durability make it cheaper than if we use, for example, other metals. So it is expensive and it can be scratched, it can be ruined, it can be broke. So BDD is a very strong. And also the low background current means that this is this is 1.31 ppm H2S detect on BDD, but this is without H2S gas. So the low background is I mean that it is a very, very low without H2S gas. So compare with GC, the position of the background is not like this. The position of the background of GC is more higher than BDD. So that's what I mean. Okay.
Okay, thank you. I think it's clear. Let's move on to the next question. This is from Yisrael. So he asks two questions. First, how you confirm BDD from SEM image? Is there any calorimetry analysis to confirm BDD? And second, how long working electrodes to detect H2S? I mean, how is the durability? Can it used for a long time?
Okay. For the same image, sorry, I would like to open this because a BDD is stable. So our BDD is stable, and just like the, I don't bring the example. So we don't use any temperature condition. So we just make it in the same image, in the same instrument, just put it and then took a picture. So we don't use any calorimeter or something. And the high durability, what do you mean? Please, can you once more? The second questions.
Okay, maybe it's about how long can you use it?
Okay. So maybe I already answered that this is the high durability. So we can detect it. We can detect it as soon as we took as soon as we bubble this electrolyte and then check the signal, and it's very fast. And also, once you made one BDD, you can make it very, very long time. I made it in 2019, in the early 2019. Still, I use the same BDD to detect many, many gas, and it's still stable. Yes.
Okay, thank you, Yunita Sensei. Maybe only two questions that I can ask to you. For the rest of question, maybe you can write it in the chat box, and I will deliver it to the audience. Okay, is that okay, Yunita Sensei? Because we have a limited time actually.
Okay, I will stop the share. How I stop this share?
Up your Zoom, maybe top of the Zoom. Yep. Okay. Thank you, Yunita Sensei, for your presentation. So we move on to the third speaker, the last but not least. Let me introduce you to the third speaker. Okay, he is Dr. Gauthaman Krishnan. He is now a postdoctoral researcher school at Engineering Monash University, Malaysia. He got her formal education at Madurai Kamaraj University for bachelor degree, Gandhigram Rural Institute for his master and PhD degree. He has interest research in synthesis, characterization, and surface modification of bimetallic nanoparticles. And amazingly, he got a lot of awards in best paper. For example, in 18 International Symposium on
Rara Sensei, no sound.
Is everything okay?
Miss Lala, maybe your internet connection is not good right now.
I think there is some trouble in ITK headquarters, so maybe Dr. Gautaman, please, you can start your session.
Yeah, thank you. Yeah, can you see my slides?
Yes, I can see your
Yes, we
slide.
can see it, Dr.
Thank you,
Gautaman.
thank you, thank you, thank you so much. And good afternoon to one and all present here. Honorable Director of ITK and Honorable Professor Masato Tobinaga, the organizer of Sakura Exchange Program, and my supervisor, and the organizers of this second international webinar with Sakura Science and Engineering Program, and from the Institute of Technology Kalimantan, all the organizers, thank you so much for this wonderful opportunity. So myself, NSK Gautaman, actually I am currently doing my postdoctoral research at Monash University, Malaysia. I am one of the alumni of the Sakura Science Exchange Program in the year of 2015 with Professor Masato Tominaga at Kumamoto University. When he was in Kumamoto University as a full professor. And thank you, Professor Masato Tominaga, for this wonderful opportunity. From this, actually, I learned so much thing from this Sakura Science Exchange Program, and also I learned the carbon nanotube synthesis and their applications with your lab and colleagues. Yeah. So this is my colleague at the time of the Sakura Exchange Program, Miss Opa. She is also from Indonesia, and the friends Sasaki, Nahakama, Nahakawa. So those people helped me a lot, and yeah, helped me a lot at the time of my Sakura Exchange Program. Thank you, one and all, for that opportunity. And this is Professor Masato Tominaga when he was in when he visited India, and we had a nice trip to Kodaikanal, and that is unforgettable memory. Thank you, Professor. Okay, so the Gandhiram Rural Institute from India. This is where I got my PhD. This is my professor, my research supervisor, Professor S. Abraham John, and this is my our research group where we work fruitful research and really well supportive friends, Dr. P. Arul, Dr. Sindhuja. They got the Sakura Exchange Program offer under Professor Masato Tominaga. Also, Dr. Sankar, Dr. Loganathan, they helped me a lot, Dr. Karthikeyan, everybody. So it's a fruitful research team. Really, I enjoyed a lot. I learned a lot with this group, and everything start from this research group. Okay, thank you. I also acknowledge my acknowledges to Professor S. Abraham John, my research supervisor. Okay, so these are my some research activities. The first one is metal oxide bimetallic nanoparticles, fabricated electrodes, anisotropic nanostructures for ACRS applications, carbon nanomaterials such as carbon nanotubes, graphene, carbon dots, carbon quantum dots, graphene quantum dots, and carbon nanoanions, as well as the nitrogen doped carbon materials. modified electrodes, then MOFs, metal organic frameworks, and their composites in electrochemical sensors, and then metal nanoparticles and carbon nanocomposites for energy and environmental applications. So these are my research activities, and also I am working with this research area. So outline of this topic is the synthesis of nanomaterials such as bimetallic nanoparticles, carbon nanotubes, and then carbon nanoanions, and their fabrication on electrode surface by different approaches, and then their environmental applications such as the electrochemical sensing of some environmental pollutants. Before moving to that topic, so we are all well aware of the metal nanoparticles. Okay, metal nanoparticles exhibiting peculiar property for catalysis, and also depending on the size and the shape of the nanomaterial, metal nanoparticles exhibit the peculiar SPR band. So by using the SPR band, we can tune the property of the metal nanoparticles, and the applications also we can tune. Okay, those are metal nanoparticles. The bimetallic nanoparticles is the combination of two metal nanoparticles. So two metals. Okay, bimetallic nanoparticles have received huge attention because of their extensive use in the field of catalysis and sensing, magnetic and electronic devices. There are different types of bimetallic nanoparticles: cluster in cluster, core shell, and random alloy nanoparticles. The bimetallic nanoparticles generally synthesized by two approaches, that is core reduction and successive reduction. So core reduction means take two metal precursors, and with the help of the reducing agent, the two metal precursors are combined to form the bimetallic nanoparticles. The successive reduction is reduction of one metal nanoparticle followed by the another. So this is the successive reduction. So in these terms, the bimetallic nanoparticles can be synthesized. And the carbon nanoparticles, carbon nanomaterials. So we know very much about graphene. So graphene is a 2D structure. It's a sheet-like structure. 2D sp2 bonded sheet-like structure. And it becomes a promising material for electrode fabrication due to its distinctive electrical conductivity and a high surface area. So generally, graphene is synthesized from graphite to graphene oxide, and then exfoliated graphene oxide, and can be reduced to reduced graphene oxide, or it can be simply called graphene. And then carbon nanotubes. So carbon nanotubes are graphene layers, and they are rolled into a cylinder of tens of nanometers in a diameter to form a hollow cylinders of carbon atoms. So carbon nanotubes can be classified into single walled, double walled, and multi-walled also. And then the peculiar property is N-doping, that is nitrogen doping. So doping of heteroatom leads to a peculiar property of the carbon material. Here, the nitrogen doping, that is the lone pair electrons of nitrogen atom form a delocalized conjugated system with the sp2 hybridized carbon network, which results improvement in reactivity and electrocatalytic performance. So the next material I want to discuss here is carbon nanoanions. So carbon nanoanions are relatively new carbon addition to the fullerene family, consisting of concentric graphitic rings, which mimic the anion morphology. So that the name comes from anion morphology. It is carbon nanoanion. The unique multi-shell cage-like structure, concentric graphitic rings, and exposed graphitic edges of carbon nanoanions enhance the efficient charge transfer process in the catalysis. So they enhance the electrical property, and they act superior one in the electrochemical sensors. Okay. So the another one material I want to discuss here is metal organic frameworks. So simply we call MOF. So MOF are formed via the coordination between metal ions and organic linkers. So metal ion and organic linkers are linked together to form the metal organic framework. MOFs are belonging to a distinct kind of flexible crystalline porous materials with diverse dimensions and various morphologies. The dimensions, so MOF can be exhibited in a 2-dimension and a 3-dimension polymer network also. The high porosity and huge surface area of MOFs are beneficial to the highly efficient detection sensitivity. So the MOFs have high surface area, highly porosity, and high crystallinity, and we can tune the structure of the MOF by varying the organic linker and the metal ion. Also, the MOF possess the luminescence property, and it can be used in the photocatalytic applications also. And then the very important, the first speaker Karthika, Ms. Karthika Sensei, yeah, explained well about the electrochemical sensors and the biosensors, the device that give information about the composition of a system in real time by coupling a chemically selective layer to an electrochemical transducer is known as the electrochemical sensor. The electrochemical sensors have more advantages because the electrodes can sense the material which are present within the host without doing any damage to the host system. And we can sense the trace level from this electrochemical sensors. And the chemical energy of the selective interaction between the chemical species and the sensor is transduced into an analytically useful signal. Electrochemical sensors are easy to miniaturize and integrate into automatic system without compromising analytical characteristics. So the electrochemical sensors are superior than the other sensors. Okay. So we have synthesized the materials, carbon nanomaterials, metallic nanoparticles. So for the fabrication of electrochemical sensors, the synthesized nanomaterials must be fabricated on the electrode surface. So via the self-assembly approach, or drop casting, spin coating, Langmuir black jet, dip coating, electrolysis deposition, electrode deposition. So different techniques, different approaches were utilized for the fabrication of materials on the electrode surface. And here the self-assembly, first one is the self-assembly using the linker. So generally the gold nanoparticles are attached on the electrode surface via the linker, thiol linker. If any thiol linker, the SH AU-S bond is very actually very very know about it, that AU-S band very well. It is a familiar one, AU-S band. Then, so if you want to attach the gold nanoparticles on the electrode surface, we can use the thiol linker. If you want to attach the gold nanoparticles on the glassy carbon electrode, then you can use the AU-N band, that is the amine linker you can take. So likewise, we can different approaches for the linkers, thiol linker and the amine linker. So we can also use the spaces and some drop casting technique, spin coating technique, and dip coating technique also we can use. Then the electrolysis deposition. So electrolysis deposition, electrode deposition, two kind of deposition techniques. Electrode deposition with the help of applied potential, the metal nanoparticles or any materials can be deposited on the electrode surface with the help of applied potential. Electrolysis deposition, there is no electric current. So there is a redox behavior. Redox behavior, that is electrochemical redox potential, use the material reduction on the electrode surface. Without any electric current, the material can be deposited on the electrode surface. So these things we are going to see in this chapter. Okay, then, so what is the need of sensing the environmental pollutants? So environmental pollutants are harmful to the human. Also, many industries or many agro products contain a lot of pollutants, like so from the industries there are dihydroxybenzene isomers like hydroquinone, resorcinol, catechol, and some sulfate containing, nitrite containing pollutants, then the hydrazine. So phenolic pollutants, they are all from the industries, and they are merged with the water, that is field water, and they are harmful to the agro products, and it also leads to the harmful to the human also. So it is highly essential to detect the environmental pollutants from the environmental water samples or any agro products. That is need for now, because many virus, many bacterial infections are all from water bodies and agro products. So at this pandemic situation, we must know how to detect the pollutants and how to avoid this pollutant containing water and products. So this is very much important. Okay. So the first one is silver copper bimetallic dendritic nanostructures fabricated electrode for the detection of hydrazine. Okay. So here we use electrodeposition as well as electroless deposition. So we can combinedly called electroless deposition. So here the copper nanostructures are electrodeposited on the FTO surface, and then the Ag nanoparticles are electroless deposited on the FTO surface. So combinedly, the AgCu dendritic nanostructures were deposited on the surface, electrode surface, and it can be utilized for the sensing of hydrazine. So copper nanostructures can be deposited on the electrode surface by electrodeposition method with different applied potential. So ranging from plus 0.1 volt to minus 0.6 volt. So go beyond the negative potential, the size of the nanostructure is getting down. So at plus 0.1 volt, there is a very well cubic structure, and then spherical, and then dendritic structure, and then prickly nanostructures. So different applied potential, because there is a relation between the applied potential and the formation of the nanomaterials. At a very low applied potential, the formation of nanomaterials is very, very low, because there is a destruction of the formation, and it is completely destroyed. The formed nanostructures are completely destroyed, so that there is very small size nanomaterials are formed. At different deposition times, so we can take, actually, we are focusing the dendritic nanostructures because open porous structure and high porosity and high surface area. We have focused the dendritic nanostructure at a different deposition time. At 400 seconds, there is a well-formed dendritic nanostructures, and we utilize these nanostructures for hydrazine oxidation. Here, the dendritic nanostructures D exhibited high electrocatalytic activity towards hydrazine oxidation, and this electrode is highly sensitive from 10 micromolar to 150 micromolar addition of hydrazine without changing the oxidation potential, and a very linear curve. And then the deposited copper nanostructures deposited electrode is immersed in the solution containing only silver nitrate. There is no any reducing agent, and there is no applied potential. So it's very interesting that the silver nanostructures were covered the copper nanostructures. There is a formation of silver copper bimetallic nanostructures. See, when we take the copper nanostructure, there is a copper nanostructure, and there is a formation of silver over the copper. When you take the spherical, there is a spherical, but the silver nanostructures were covered the copper nanostructures. Similarly, dendritic nanostructures are also formed. See that different applied potential, different nanostructures were obtained. Also, at different timing, only 20-minute immersion time gives the plentiful and fruitful formation of Ag copper bimetallic nanostructures. So within 20 minutes, we can form the bimetallic nanostructures on the electrode surface. So it can be characterized by participants. Please mute yourself.
Enak banget, langsung banget.
Okay, thank you. Okay, the formed bimetallic nanostructures can be characterized by XPS and XRD. So in the XPS, there is a formation of Ag3D band and Cu2p band, confirming there is a formation of both copper and silver in the metallic state. That is the important, because we take metal ions, that is Ag plus ion, but here obtained is a silver nanoparticles. So this is important. Okay, and then there is a formation of the AgCu is confirmed by the Ag core and copper shell. And then the modified electrode is utilized for hydrazine determination. Here we already know already discussed about the copper nanostructures for hydrazine detection. So over the copper nanostructures, silver copper bimetallic nanostructures exhibited higher electrocatalytic activity towards hydrazine with a limit of detection of 0.12 nanomolar with a superior sensitivity of 3722 microampere per millimolar per centimeter square, with the detection range of 20 nanomolar to 50 micromolar. So this paper was published in ACS Sustainable Chemistry the year of 2018. So then carbon nano anions. So carbon nano, nitrogen doped carbon nano anions fabricated electrode for the simultaneous determination of dihydroxybenzene isomers like hydroquinone, catechol, and rasacinol. So very simple procedure was employed for the synthesis of nitrogen doped carbon nanoids. We take only acetonitride flame pyrolysis method at 1100 to 1300 Kelvin, followed by condensation, leads to the formation of carbon nano anions. It's a very much graphitic concentric circles followed by the concentric ranges of anions, confirming the formation of carbon nano anions. And it was characterized by HRTM images, the CNO and nitrogen doped carbon nanoanions. So the N doped carbon nanoanions give the sp2 hybridized material with the concentric ranges like anions, so that the name comes from that carbon nanoanion. And it was characterized by Raman and XPS also. The presence of nitrogen group is confirmed from the N1s spectra, and the D by G ratio confirms the sp2 hybridized the highly graphitic carbon material. Okay, so the material was fabricated electrode. Actually, I forgot to inform. Okay, so the electrode fabrication here, there is no electric current, there is no electrolysis deposition. We just immerse the electrode into the solution containing the carbon nanoanion. There is a pi-pi stacking and electrostatic interaction leads to the formation of carbon nanoanion on the electrode surface without any linker. Without any linker, there is no linker, only electrode immersed on the immersed into the solution. There is a formation of carbon nano anions on the electrode surface.
Dr. Gautaman, maybe can you make it faster?
Yes, okay.
Because the time is limited. I'm sorry.
Okay, thank you. So the modified electrode is utilized for the detection of hydroquinone, catechol, and rasacinol. So these are all the pollutants from the industries, and the modified electrode can simultaneously detect hydroquinone, catechol, and rasacinol. Okay, then the single-walled carbon nanotubes. It is very much interesting work. Actually, where I have learned from Professor Masato Tominaga's lab at Kumamoto University, and the paper was published in Journal of Electronautical Chemistry. So with the acknowledgement of Sakura Science Program. So, okay, so here we take the carbon nanotubes. Already Karthika Sensei explained the synthesis of carbon nanotubes on the gold wire. Okay, so here carbon nanotubes were synthesized and characterized by Raman and XPS. Okay, here we follow the electrolysis deposition for gold and gold platinum bimetallic nanoparticles. The carbon material is capable to reduce gold. Okay, so that we just immerse the electrode into the solution containing gold uric acid solution. So without any linker, any reducing agent, carbon gold nanoparticles were deposited on the CNT surface. Likewise, the AU nanoparticles formed electrode is immersed into the platinic acid solution. There is a formation of gold platinum bimetallic core-shell nanoparticles in the electrode surface. So we utilize the electrode for the detection of glucose and hydrogen peroxide sensing. Okay, the final material is metal organic framework. So metal organic framework, we take the copper metal organic framework, decorated graphene oxide sheets for the detection of nitrate in environmental water samples. Okay, so the synthesis of copper MOF is followed by ultrasonic synthesis, ultrasonic assisted synthesis. We take graphene oxide and copper salt. There is a formation of copper metal ions on the graphene sheets, and then solvothermal with azelaic acid gives the copper MOF on the graphene oxide surface. Here, what is the why we need graphene oxide? When we take copper MOF, the size is very large, but when we react the copper MOF with graphene oxide, the size is controlled very well. See the difference in size. The size of copper MOF is here large and very controlled size. So this is a size controlled synthesis of copper MOF. So graphene oxide layers control the size of the copper MOF. So this is the interesting point here, and we utilize the modified electrode for the synthesis of for the sensing of nitrite in environmental water samples. Here, the graphene oxide copper MOF containing material exhibited higher electrocatalytic activity towards nitrite from the range of 5 micromolar to 50 micromolar addition. Okay, so this is my concluding remarks. So different fabrication techniques were employed for the fabrication of metallic and carbon-based nanomaterials. AGCU dendritic nanostructures were fabricated by electrolysis deposition mechanism and utilized for hydrogen detection. N-doped carbon nano anions were synthesized by flame pyrolysis method and fabricated on GCE for DHB isomers. AUPT bimetallic nanoparticles were fabricated on SWCNTs for H2O determination. Copper MOF was decorated on GO sheets for the trace level determination of nitrate. And surely the strategies followed here could open promising new avenues for designing novel functional materials for environmental applications. So I wish to express my deepest acknowledgements to Professor S. Abraham John, my research supervisor, Professor M. Masato Tominaga from Sakura University, to give me the opportunity to access the Sakura Sciences Exchange Program. Professor J. Jin Shim from Yangnam University, South Korea, so my former postdoctoral supervisor, and Professor Janet Lim Hong Ni, University Putra, Malaysia, my former postdoctoral research supervisor, and Dr. P. Arul, so my friend supporting me, currently doing postdoctoral research at National NTUT, Taiwan. Okay, also I express my acknowledgements to Sakura Science Exchange Program and all the funding agencies. Thank you so much.
Okay, thank you, Dr. Gautam. I apologize for the technical problem here, but here I am. I come back again. I'm sorry. So everyone who wants to ask question to Dr. Gautam, you could send me the message via chat box, or you can raise hand if you want. Is anyone question? Okay, maybe I could maybe Hiskia Alpha? Hiskia Alpha? Okay, maybe we can wait for Hiskia Alpha to join with us. Tominaga Sensei asks you a question, Dr. Gautaman.
Yeah.
So the question is, what is an advance of anion carbon compared with MWCNT?
Yeah, actually, Professor, the MWCNTs, the defects are high when compared to the SWCNT also. Okay, the defects in MWCNT is high, but when you use the carbon nano anions, the sp2 hybridization is very well. So the graphitization is high. That is the very important thing we follow here. The open pore structure. So when compared to the MWCNT, it is an open porous structure and a highly graphitized one, and the concentric rings gives the highly open access to the analyte to access here. That is the open porous. So that when compared to multiple carbon nanotube, carbon nano anions, a little superior. then multiple carbon nanotubes.
Okay, thank you very much. I understand.
Yeah, thank you, Professor.
Okay, thank you, Professor Tominaga. Oh, here it is. A question from Hiskia Dewanto. Dear Dr. Gautaman, what is the advantages of onion-like structure to other structure in its use as sensors? Also, does it only have use in sensor or it has other application? Thank you.
Yeah, so just now I explained to Professor Masato Tominaga the advantages of carbon nano anion, like graphitization and sp2 hybridization and open pore structure. And these are the advantages of carbon nano anions. So these advantages create the electrical property of the material, and there is a highly electrical property. There is a charge transfer resistance to electrode and electrolyte, open pore structure material. So this is the advantage. This can be utilized in supercapacitor application also. There are some reports are also available by utilizing the carbon nano anions for supercapacitor applications.
Okay, thank you very much. I think your onion structure has much interest to our audiences actually.
Thank you.
Okay, thank you, Dr. Gautaman. Maybe we have only 2 questions for you. The rest of the question, maybe I would like to send to you and you could write the answer and I send email to the audiences. Is that all right?
Yes. Thank you.
Okay, thank you. So this is the end of our meeting. I would like to appreciate all the speakers who deliver such an amazing speech. Therefore, I will present to you the virtual plaque for all of you. Please accept it. So here it is, a placard for Kartika Noraga, Yunita Triana, and Dr. Gautaman. I will send it to you. The actual one, actually, this is virtual because we are in online, but actually I will send to you the actual one to your house, exactly to your country. Thank you very much.
Thank you.
Okay, that's... Okay, that's too bad. We are at the end of the speech session. Hope you get the inspiration from today's event. I deeply apologize if there are inconvenient words or technical problems. I am Gustil Mindya Nurtajala. See you at the next event. Bye-bye.
Okay, thank you for the amazing.
Maybe
Okay,
the committee just please wait in the Zoom meeting to make small observations.
Okay, yeah. Thank you for the amazing speeches from all the speakers and lively discussion from all the participants. So thank you also to our brilliant moderator today, Gustiu Mindya Nurtajala STMT, for leading the speech session perfectly. Also, I want to remind all of the audience to fill out the attendance that our committee provide in chat box. On behalf of committee, I especially want to appreciate Professor Dr. Masato Tominaga, who has taken the time and gave full support in today's collaboration event. Also, thank you to all 3 of the invited speakers, Kartika Noraga, SSI MSI, Yunita Triana, SSI MSI, and Dr. Gautaman Krishnan, who warmly accepted our invitation. I also would like to send a big gratitude to Department of Materials and Metallurgical Engineering of ITK for the opportunity given to me as the MC today. So I feel so honored. Thank you very much. Also, many thanks to ITK's rector, vice rector, head of faculties, head of departments, and all the committees who strongly supported the event until it is realized. Thank you again for all the participants who attend the second international webinar. If you need more information or question about the webinar, you could contact Mr. Ade. The mobile phone will be shown in the chat box. And again, as mentioned by our moderator today, if you have questions for the speakers, you could send us email to mme@itk.ac.id. Once again, mme@itk.ac.id. Finally, now we are in the end of the webinar. Hopefully, this event could give you inspiration and new insight about the recent technology on material science and engineering, especially on sensing application. We apologize if there are any mistakes from the committee. So we need your feedback to improve our quality of event. Thank you very much once again for your kind attention. Hope you have a great day. See you on the next webinar. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Naga Sensei. Thank you so much. Yunita Sensei.
Sensei, maybe the speaker and the committee just keep in Zoom line first, okay? Don't out.
Okay. Harutika Sensei, Harutika-san, thank you so much. She's still there. See you again, Dr. Gotaman.
Thank you, Professor, for this chance.
Yeah. So
Dr.
you published a
Gotaman.
very nice paper. It's a journal. Yeah.
Yes, Professor.
Yeah, you become real good, excellent researcher now. Yeah, I hope you get a position in India or some good place.
Thank you, Professor. With your blessings. Thank you. Thank you so much.
Dr. Gotaman, actually there is one question. I will send you to email, okay?
Okay, please.
Thank you. Because so many questions.
Yeah.
So I see the participants is stable and on 350 people.
Yeah,
Yeah,
around 350.
Thank you guys for your all hard work.
Thank you very much, all of the volunteer students. I don't know your name, but thank you so much for your effort.
Just please wait a moment because the participants still 173.